Hello, everyone.
Hello.
Hello.
Hello. So is everyone able to hear me?
Yeah.
Yes.
Okay, great. Okay.
Yeah.
Okay, so let's get started. So in this tutorial, we will be covering exercise 5.1 and exercise 5.2. So let's get started with it. So I'll share my screen now.
You said 5.1 and 5.2?
Yes, 5.1 and 5.2.
We haven't done 5.2 yet.
Sorry?
We haven't done 5.2 yet.
No, I'm saying 5.1 and 5.2, not 3.
Yeah, that's what I said. Like, we haven't done 5.2.
Oh, you haven't done 5.2 yet?
Yeah, because he only taught 5.1.
Just give me a minute. Let me see what the professor said. So before 5.1, what did you guys cover?
Like 2.3, 2.4, and 2.6.
2.6, something like that.
Yeah.
And then afterwards, it's 5.1 only.
Yeah.
So no 5.2.
No, because like he taught 5.1, like the induction stuff mostly.
Okay, let me just see quickly. So in the communication that I received from professor, he told me to cover 5.1, 5.2, but since you guys haven't covered 5.2, so probably in this tutorial we can only go over 5.1, and then later in the next one we can cover 5.2. How does that sound like?
That sounds good.
Okay.
Okay, great. Okay. Okay, so let me share my screen here. Okay, is everyone able to see my screen?
Yes.
Okay, great. Okay, so this is the first question from exercise 5.1. It's on page number 350. So this exercise here, basically, it's so you have to prove the following questions using the proof by induction. So induction, we have two steps. So first the basic step, and the other one is inductive step. So let's take a first example. So there are infinitely many stations on our train route. Suppose that the train stops at the first station, and suppose that if the train stops at a station, then it stops at the next station. Show that the train stops at all stations. So here we will suppose that here this is a function p of n. Be the statement that the train stops at station n. So this p of n represents that this train stops at station n. Okay. Now we have to define the basic step and the inductive step. Basic step and the inductive step. Now in the basic step, so basically in the basic step we have to take the smallest instance, the smallest thing that we know about it's true. So we know that suppose the train stops at the first station, so we know that p of 1 is true because we are told that it stops at the first station. So according to this assumption, p of 1 would mean that train stops at the first station. Okay. So this is the basic step. Now, in the inductive step, we will say that we are told that P of n implies that P of n plus 1 for each n greater than or equal to 1. So here we are told that train stops at a station, then it stops at the next station. So this is how it will be worded. Therefore, by the principle of mathematical induction, we can conclude that P of n is true for all positive integers. Okay, just n. Okay, so we know that based on the question, we know that the train stops at the first station, which is our basic step. Then we know that the train stops at every other station, which is the next station. So this is our inductive step. And therefore, we can conclude that by the mathematical induction that P of n is true for all positive integers. Therefore, that's proved. Okay. Any questions? Okay, if no question, let's move on to the next question here. Okay. So we have this question number 5 here, and then we have to prove that 1 squared plus 3 squared plus equals to n plus 1 to n plus 1, where n is a non-negative integer. Now here, we can say that let P of n be this part here, 1 squared plus 3 squared plus this thing over here. So 1 square plus 2 square three square plus 5 square plus 2n plus 1 square equals to n plus 1 multiplied by 2n plus 1, and then 2n plus 3 divided by 3. So this whole statement over here, this we assume that Pn represents such a statement. Now we have to define our basic step. So what's going to be the basic step here? Basic step is, so if we introduce n, where n is a non-negative integer, well, the smallest non-negative integer is 0. So if we plug in 0 in the places of n, then what we get is both sides equals to each other. Okay, so P of n therefore is true because left hand side equals right hand side. Okay, therefore it's true. Okay, now we have to define our inductive step. Now in the inductive step, we assume that P of k is true. Now what is K? So K is anything other than N. Okay, so here in the inductive set, we assume that basic set always covers the smallest instance from the domain. In the inductive step, we take the number which is greater than the smallest instance. Okay, so now we assume that PK is true. So then K is just copy this. Then here we have 1 square plus and then 2 K inside of N we will put in K. And then 2K plus 1, and then we also go one step further, which is plus 2 into K plus 1 square, because that will be the next number in that sequence, right? We suppose that if it's true for something, then it's true for the next thing as well. So this is what we know of, and then the next step, because this is inductive step, so in the next one, so this is going to be the next value. So we assume that this is true for this one as well. Now this will be equal to K plus 1, and then here will be 2K plus 1, and then 2K plus 3, and then the next one in this sequence will be 2K plus 2K plus 3 square. Okay, because we are adding this on the left hand side, and then if we add this on the right hand side, so this 2K plus 2 plus 1 is 2K plus 3, and then we have the whole square, so we add this there. Now this one here, this is equals to, I'll just put it on the next line. This one is equals to, we can put this on the next line as well. Yeah. Okay. Now this one here, it's equal to 2K. So we're just gonna simplify this equation a little bit. So it's 2K plus 3, and then we have K plus 1, and then we have 2K plus 1 divided by 3, and then we have plus 2K plus 3. Okay, so we basically, what we did is we multiplied this with, because this is a square, and then this is, so we just simplified this just to remove the square. Now this one here equals 2k plus 3, and then 2k square plus 9k, just nothing else, just resolving this, simplifying this, and then divide by 3, which is equals to 2k plus 3, 2k plus 5, k plus 2, divide by 3, which is equals to k plus 1, k plus 1 plus 1, and then we have 2 k plus 1 plus 1, two k plus 1 plus 1 plus 3 divided by 3. Okay, so what we did here is, so we have to prove this over here. So we assume that this statement over here, right? We assume that this is P of n. Now we have to define our basic step based on what we know from the question. So the basic step is we take the smallest number from the domain that we know. So here we know that n is a non-negative integer. So the smallest one will be p0 here. Now we have to simplify this equation for p equals to 0 here. Now by doing that, we found out the left hand side basically equals to right hand side, therefore it's true. Now since the basic step is true, we can proceed further to the inductive step. Now in the inductive step, what we did is, so we assumed this until n plus 1, or so in the inductive step we assume that this n is basically k, and then we have to define one step further, right? So it's until 2n plus 1, right? But then we have to define one step further here. So this is the one step further, and then after resolving this here, so we got up to here, which is basically representing this statement over here. So therefore we know that this left hand side equals to the right hand side here. So hence it proves that left hand side equals to right hand side using induction.
Is this a different way of solving it? Because like from the lecture, the professor told us like to first look for PK, and then we state what would be PK plus 1, and then from PK we try to get
PK? This one?
yes.
Okay.
And then from PK we try to get PK plus 1, like by equaling the right hand side of PK plus 1 with like all the calculations that we do on the left hand side.
Yeah, so basically this is what we did here as well. So here, so we have this pk, for example, pk, so pn, so if we add pn, and then we add one step further in that sequence, which is represented by pk here, right? So now what we did here is we take the left hand side, which is this 1 square until this, before this equal sign, okay? And then we define it one step further. So we know this sequence, right? So because we have already studied the sequence and series in the previous tutorials, right? So now we can assume, well, like what's going to be the next value in the sequence, right? So based on that, we figure out what this is, and this is the next step, right? And then now we have to prove that this also holds for pk, right? So we have to also make this left hand side equal, this new left hand side equals to this right hand side. So this right hand side, so we basically replace n with k here, right? And then this is basically the added stuff that we added, right? So this one here, right? So we added this one on the left hand side, and then we added this one on the right hand side to make them both equal. Okay, and then what we did is we try to balance the equation, and then we figure out, like later after we simplify, that both left hand side and right hand side are equal to each other. Therefore we prove this using induction.
Oh, okay. I see now.
Can make sense?
Yes.
Yep.
So the only difference is just the k plus 1, right? It's still, it is kind of equal, but the difference from the left hand side to the right hand side is the k plus 1.
I'm sorry, which one?
You know that you simplified it from k, you separated k plus 1.
This one?
No, in the last step, in the last,
Here.
yeah, you separated the k plus 1.
Yeah,
So
because we have to make it, you know, similar to something on that side, so that we can eventually draw a conclusion that it is equal. Right, so basically what we're trying to do is we are trying to make that of the similar form as we see in the question, right? So n plus 1, 2n plus 1, 2n plus 2, and then we have the divide by 3 at the end, right? So we trying to do that all along. Okay, so we're gonna take that equation, and then we're gonna play with it so that it fits in the form that's in the question, so that we can draw a conclusion it's equal.
I get it now. Thank you.
Okay, so here basically this n, this k here equals to n plus 1, right? So this here, this one here, k plus 1 here, or should I say k plus 1 equals to n here. So now this n here, so if we have this equation here, we have this on the left hand side, oh sorry, right hand side. So this side, right? So we reach this one based on the inductive step, right? And this is our original question, right? So if we just see this n here, right? So we just replace it with k plus 1. And then this n, we replace it with k plus 1. This n, we replace it with k plus 1. Okay. It's just a matter of equating the equation, and you will eventually reach the solution. That's it. Okay, any other questions?
2k square from?
Okay.
Hi, where did you get the 2k plus 3 square from?
Plus 3 square. Oh, this one here?
Yeah.
This one here, basically here. So on the left hand side, this is in the question. So this from here to here, right? This is given to us from the question, right? And then we figure out what could be the next term in the series, because this is an inductive step. We always think about the next one, right? So this is going to be the next term in the series, right? Right. So since we know that this is the next term, and then we added this on the left hand side, and then we added the same thing on the right hand side to make them both balance. So if we just simplify this becomes 2k plus 3 squared.
Okay, thank you.
Okay. Any other questions?
can we leave it as 2k plus 3, 2k plus 5, k plus 2? Can we leave it as that?
2k plus 3, which
Like,
one? This one?
no, this one, the second to the last line.
Second, this one?
Yeah, can we leave it as that?
We see, the thing is, we like, you can leave it like that, but then it won't be too intuitive, right? Because this one eventually is equals to this one, right?
Yeah.
But this is not in the form that we have to prove, right? So we have to make it in that form.
Oh, okay, I get it now.
Right?
Okay, yeah.
Okay, let's move on to the next question. So this is question number 9. So we have to find a formula for the sum of the first n even positive integers. So now we know the domain. The domain is even positive integers. So we will try to prove this using induction. Okay, so here, we have to basically find a formula. We don't have to prove anything. So we have to say 2, the first even positive number. Let's start with that. So 2 plus 4 plus 6 plus up, like we can take that to so many of them, and then 2 to the n, which is the general formula, and then we see that n into n plus 1. So this will be the general formula for the sum of the first n even positive integer. So if I have, let's say, I want to find the sum of first, let's say 3 positive even integers. Using that formula, it will be, so 2, so here our n will be 3. So n equals to 3, right? And then we just gonna put this in our equation, n into n plus 1, which we just found out just to prove that. So if we put 3 into 3 plus 1, which is 4, or should I say 3 plus 1, let me just write it down here, 3 into 3 plus 1, 3 into 3 plus 1, so which is 3 into 4, which is equals to 12. Okay, so now this is on the right hand side, right? So we find 12 is the answer from the right hand side, and because this is so simple that we can actually do it ourselves. So 2 plus 4 plus 6, or maybe should I say this is the value for the right hand side, and then if we say on the left hand side, if we evaluate it ourselves, so it will be the first positive number 2, the second one is 4, the third one is 6, which is equal to 12. So we know that this number here is this number here, so we also prove this, right? But the proof is coming later on in the part B. So let's move into the part B and prove this using induction. Okay. So here we have to first define the basic step. Now, for the basic step, we know that we will go with the smallest element in the domain, which is the first even number, which is 2. The first even number is 2. Okay, so we'll say 2 equals 2 based on this. So 2, and then we have this equation n plus 1. Okay, 2 equals 2. 2 equals to n into n plus 1, right? And then we'll say 2 equals to, we know that n here equals to 1, right? Because the first even number, we're taking the first number, so n 1 into 1 plus 1. So we found it 2 equals to 2. Hence, this is true. Okay, so our basic step is true. Now we will take the inductive step. In the inductive step, we'll go one step forward. Okay, we assume that if it is true for for some n, then it's also true for some n plus 1. Okay, so this is how we do inductive step. Okay, so in inductive step, we assume that 2 plus 4 plus 6 plus 2k here, and then we have this k plus 1. Okay, then 2 plus 4 plus 6 plus 2k, and then we have this one step forward, which is the 2k plus 1. This is the next element. Okay, and then this will be equals to k into k plus 1 plus 2k plus 1, which is equals to k plus 1 and then k plus 2. Okay, and therefore we have proved this here, that sum of the first and even positive integers equals to n over n plus 1 here, because we have made it in that form. Okay, so basically we start with the first even positive integer, which is n equals to 1, and then we prove that this thing over here, this formula that we just found out in part A, it is true for the basic step. So we found out that this is actually the case. This is true. And then inductive step we have to prove. So in the inductive step, what you said is, so we take the how it was in the question, and then we said, like, if this is true, if this left hand side equals to right hand side for this one, then by induction it should also be equals to this one. And then we simplified it to k plus 1 and k plus 2 here. So therefore we prove that our formula from part A is correct. So this is how you can come up with the formula and know that if it actually works or not by proving them using induction yourself.
Like normally, don't we first write the formula for pk plus 1, like before making the comparison?
I'm sorry?
Like prior doing the calculation, we would normally like put the formula for pk plus 1, like we will have pk plus 1 equals 2 plus 4 plus 6 plus 8 plus ... plus 2k plus 2 k.
Yeah, so
2.
this one here is from the question, right? So we just replace n with, so this one is just like here, right? We just replace n with k, right? And with k.
Yes, but like I think normally, like in the lectures, what the professor did, he would like also substitute by k plus 1, so you get like the right hand side, and from that right hand side, he would try to get it from the left hand side by adding k plus 1 from pk.
Yeah, basically how it could be is we have to prove that both sides are equal. So you can either start with the right hand side and prove that it actually is equals to left hand side, or you can start the opposite way. You can take the left hand side and prove that it's equals to the right hand
To the
side.
right hand side.
Yeah.
Oh, okay.
Yeah, because they are equal, right? So it
Yes.
doesn't matter
Which side we start from.
Yes.
Okay, thank you.
Okay, any other questions?
Hello.
Yeah, any questions?
No.
Okay, no question. Let's move forward to question number 15 here. So we have to, again here, we have to prove then these sides are equal using proof by induction. Okay, so doesn't matter we start from left hand side or the right hand side, the eventual conclusion is to prove them they are equal or not. Okay, so let's start with it. So we suppose that P of n be 1.2 plus 2.3 plus n into n plus 1, okay? And then this here, n into n plus 1. Nothing, just the equation in the question. I'm just writing that. N plus 2 divided by 3. So I assume that Pn represents such an equivalence, okay? Now, since we have defined this what Pn is, now let's define it, the basic step. Okay, the basic step. What's going to be the basic step? Basic step here, we know that for every positive integer n, so the first positive integer is 1. Okay, so we'll do that for P of 1. Okay, so we'll say P of 1 here is true because 1.2 plus, or 1.2 equals to, we take only the first and then we put that there, equals to 1 into 1 plus 1 1 plus 2 divided by 3, which is equal to 2, right? So if we simplify this one here, 1.2 equals to this, which is 2 equals to 1 into 2, then this 3 divided by 3. Okay, so 2 equals to 2. Therefore it's true. We know that our basic step is true. Okay, let's move on to the inductive step now. Inductive step. Now, because inductive step, we assume that if this is true for n, if something is true for n, then we assume that if something is true for n, then it's true for n plus 1 as well. This is what we basically prove in inductive step. Okay, so we assume that P of k here, pk, is true. That's why we don't use n here, instead we use k here. Then So we present this statement here, this here with P of K, and then we assume that this is true. Now what we do is we have to say that PK plus 1 is also true. We have to prove that, okay? Now 1.2 plus 2.3 plus K into K plus 1. Now this is until that we have its PK. Now we have to define the one step further. What is that step further? So the next value in line will be K plus 1 and then K plus 2. This is the further step. Okay. And then we said that we assume that since we define the one step further, so we add the same thing on the right hand side as well. Okay, so we have this n over n, this one here, just replace it with k plus 1, k plus 2 divided by 3, just, and then we add plus let me just put them in the bracket just to make it more clear. Plus we add this thing that the extra thing that we added on the left hand side, we also add this on the right hand side. Okay, now we have to simplify this. Now what we do here is we say k plus 1, k plus 2, okay, and then we have this k divided by 3 plus 1, which is equals to k plus 1, k plus 2, k plus 3 divided by 3. Okay, now this here, this one is here. If I just put them on the side here, if you will observe carefully the statement, these two here, so this one, and then this one here, these ones n here, basically if you replace in this statement, if you replace n with k plus 1, right? If you put n equals to k plus 1 over in this one here, you will get this one here. And this is actually what we are proving here, because we are defining this step when it's one step ahead. So we're proving that, which we have proved. Okay, so therefore we have proved using induction. Any questions? Okay, if no questions, let's move onwards. So this is the question number 19 here. Maybe I can just reduce it a little bit. Okay. Okay. Now here we have Pn be the statement. So now we have this function Pn which represents this statement over here. And then we are told that where n is an integer greater than 1, we know the domain of n, so it's integer greater than 1. What is the statement P2? Again, P2, this is also going to be basic step. So P2, nothing special here. We will just replace this statement with 2 wherever it has n. So 1 plus 1 over 4 plus 1 over 9 plus dot plus 1 over 2 square is less than 2 minus 1 over 2. Okay, so this is going to be our P2. Next part, B part. Show that P2 is true, completing the basic step for a proof by mathematical induction that Pn is true for all integers n greater than 1. Basically, what we have to do is we have to define the basic step for this proof here. So what is the basic step? We know that this is true because we have basically just proved it, right? So we know that this is true because 5 over 4, right? So if we evaluate this one here, it comes up to 5 over 4, right? And this is less than, then if we evaluate this, 6 over 4, right? So if we basically inject 2 in this statement over here, and then what we do is 5 over 4 is what we get on the left hand side, 6 over 4 is what we get on the right hand side, and then therefore we know that this is true because 5 over 4 is less than 6 over 4. In the part C, what is the inductive? So we have to prove what the inductive step is. So we have to think of one step ahead. So inductive step here. So in the inductive step, this is going to be 1 plus 1 over 4 plus, we can just skip 1 over 9 here and then put the dot, or we can include up to you guys. Then 1 over k square less than 2 minus 1 over k. Okay, so we just replace this wherever it says n, we replace it with k. Okay, so this is going to be the assumption for the inductive step. This is the hypothesis or the assumption for the inductive step. Okay, next is part number D. What do you need to prove in the inductive step for proof of mathematics that Pn is true for all integers n greater than 1? So we know that for each k, right, which is greater than or equal to 2, that P k implies P of k plus 1. In other words, we want to show that assuming the inductive hypothesis in step C that we did here, inductive hypothesis. This is here in step C. Okay, next step. Question number E, part number E here. Complete the inductive step of a proof of mathematical induction that Pn is true for all integers n greater than 1. Now here we have already defined the basic step. We know what is the hypothesis step here, right? And inductive hypothesis here. And then what we have defined here is for k, so we have here 1 plus 1 over 4 plus 1 over k square plus the next one will be 1 over k plus 1 square. Okay, now this one is less than 2 minus 1 over k. 2 minus 1 over k plus 1 over this extra step here. Now we have to manipulate this to somehow prove that the left hand side is less than equal to the right hand side. Or what you can do is you can take the right hand side and you can prove that this is greater than left hand side, okay? Any questions?
So is this the final answer?
This one is basically the hypothesis step. In the part B, we define the basic step. In the part C, we define inductive hypothesis, right? And then this one here will be basically the inductive step. Okay. Now you have to simplify this here, right? To prove the left hand equals to the right hand. It's not difficult. It's basically just how we have done before, right? So we've been keep doing this in this part here. We have done this in this part here. Then we have done this over here as well. So it's gonna be just the same thing in the same way. Any questions? No questions, so let's move on to the next part, which is question number 23. So we have to prove for which non-negative integers n is this. Prove your answer. So we have to prove it using the so here by okay. So if we observe the equation and we take value for n equals to let's say 0, 1, 2, 3, right? And then let's say if we evaluate this for n equals 2 in this equation here. So let's say that n equals, when n equals to 0, this statement here, 2n plus 3 is less than equals to, this is less than equals to, okay, maybe this one is better, to the power of n. Okay, so this one will become 2, 0 plus 3, which is less or equal to the power of 0. Now this one here, now this one here, 2 into 0 is 0 plus 3, so this is 3 less than or equals to 2 to the power of 0 is 1. So 3 is less than equals to 1, therefore it's not true, therefore it's not true when n equals to 0, right? So this is the first non-negative integer, 0, right? So we prove for 0, this equation does not hold. Okay, and then we likewise we can prove for let's say 3 as well. I'm just gonna copy this. So here when n equals to 3, so 2 into 2n, right? And then we can just replace the 0 with 3, and then 2 to the power 3 is 8. 8, and then this 3 is 6, 6 plus 3 is 9. 9. You see 9 is less than or equals to 8. Therefore, it's not true when n equals to 3. Likewise, we can also prove for 0, 1, 2, 3. So for the first 4 integers, we can prove this is not true. So we know that for these ones, this equation does not hold. Now we have to prove it. So we said let's p the power of n be the proper position that this in holds for positive integers and inequality proposition. Okay. Now we have P of 4, right? We already proved until P of 3, this is not true. Now let's start with P of 4. Now this basic case, so now this is going to be the proof when, so for the first value, the smallest instance for which this statement is true is P of 4, okay? Is true because 2 here, just copy this. So 2, then we replace this 4, and then we replace this with 4, right? Which we know that 11 because here 11 equals to or less than 2 to the power of 4, which is 16. So therefore this is true. Therefore the basic step is true. Okay, let's move on to the inductive step. For the inductive step, we assume that P k is true. Our P of k is basically this thing here, but instead of n, we just put k here, okay? This one here, P over k is true So just for your reference, I can just put it quickly what P of K is. P of K is this here. This is whatever P over K is. Okay, so we assume this is true. Now in the inductive step, we have to define P over K plus 1. So we assume that this is true. Now we have to prove that it's also true for P of K plus 1. Now what is going to be P of K plus 1? Now, so we have this 2K plus 1 plus 3. Right, we're just replacing this K with K plus 1. Okay, equals to equals and 2 to the power of K plus 1. Okay, so this is the left hand side, and we are saying that this is less than or equals to this right hand side here. Okay, but because K is greater than equals to 1, 2K plus 2 is less than or equals to 2K plus 2K, which is equals to 2 to the power of K plus 1. Therefore, we know that inductive step is also true. Any questions here?
Sir, can you explain the last step?
Okay, basically what we did here is, so we have this, so this one you get, or this one did you get?
Yeah.
Okay, so we have this PK in the inductive step. This is our inductive hypothesis is this, okay? And then we have to be proved. We have to prove this thing here. And then we are just proving this thing here in this step here. So what we did here is, so we know that K is greater than equals to 1. We know that because it is a non-negative integer, right? So therefore, K is greater than equals to 1. Now we said that 2 to the power of K plus 2 here. Maybe if I can just space it out here. So 2 to the power of K plus 2 here, right? 2 to the power of K plus 2 is less than equals to 2 to the power of K. So this thing over here, right? This thing over here, this is actually equals to 2 to the power of K plus 2 to the power of K. Okay, so we write this thing here, right? This thing here as this thing here on the right hand side. Okay.
Okay.
Okay, and then we said that this is less than or equals to 2k plus 1, the left hand side. Therefore, we know that our inductive step is also true. Okay, let's move on to the last question. So in this question number 31, we have to prove that 2 divides n squared plus n whenever n is a positive integer. Now we know some property of n, that n is a positive integer. Now the smallest positive integer that we can think of is 1, right? So let's define our basic step. Now what is the basic step? We said a 1 here. We will just replace 1 and we take n equals to 1, and then we say that 1 to the power square plus 1, right, which is equals to 2, right? Now this is divisible by 2, therefore basic step is true. Okay, therefore our basic step is true. Let's move on to the inductive step. Inductive step. Now in the inductive step, what we have to assume is, so inductive step has inductive hypothesis. In the inductive hypothesis, we assume that this here, k square, we're just gonna replace n with k, right? So it's a k square plus k is true. This is our inductive hypothesis. Now we have to prove that k square, k plus 1 square, because we have to have k plus 1. Okay, k plus 1 square plus k plus 1 is also true. Okay, now how can we prove this? So if we copy this, put it down here, we know that k plus 1 square can be written as k square plus 2k plus 1, and then this opening this up, k plus 1. Now this is equals to k square plus this 2k plus 3k plus 2. Right? This is one way, but we're gonna do it in this way. So k squared plus k, so we're just gonna group this together because we're gonna make it like this, k squared plus k. So we will take k square here, k square plus k, and then we can group this 2k, 2 into k plus 1. Okay, now this here is equal to this one here. Now we did it because we want to prove that this basically here is divisible by 2. Remember, we have to prove that 2, this here is divisible by 2. Okay, so it can be clearly seen that the sum of a multiple of 2, so this is a multiple of 2, right? And then we are adding it to some number here by the inductive hypothesis, by the hypothesis, and a multiple of 2, hence it's divisible by 2 and proved. Okay, so basically here we have this k plus 1 and this is a multiple of 2, right? So we know that this here, this one here is divisible by 2. By 2 because then this 2 will just go off and it will be k plus 1. Okay, now how do we know that this one here is divisible by 2 or not? No, because here it says in the question that n squared plus n, right? So this is, we've already assumed that k squared plus k is true, which means that k squared plus k is divisible by 2. This is our assumption, and this we know that this is true. Therefore, altogether we know that this whole thing is divisible by 2.
Miss, sir,
Yes.
are you going to do induction by finite sets?
Induction by finite sets.
Yeah.
So here we have already, yeah, in that term, like in finite sets, when you say a finite sets, what I am thinking about finite sets is it's not it's a set where the domain is restricted. It doesn't contain all the elements, right? It only contains like a finite number of sets, numbers in the set, right?
Are you going to
Right.
Are you going to do any induction exercises related to finite sets?
Finite sets, maybe it's coming in exercise 5.2 here, but since you guys have not covered that, did you guys cover that in 5.1?
Yes.
Yes.
In that sense, this one here, it's actually finite sets, right? Because here we are not considering n to be, you know, like true for all real numbers, right? So we have finite sets of n, which we are saying is a positive integer, right? It doesn't contain infinite numbers. It's a finite set of positive integers, right? And then we're doing the induction on those numbers. So this is the induction
We
by...
actually meant sets. We meant sets like the ones that we took in chapter 2.
But this chapter is about the induction, right?
Yes, but like in the lecture, like we cover something like mixing both chapters. Something like we are supposed to prove that.
Maybe in the next exercise
both
we have some
chapters,
example for that. Okay, maybe in the next exercise we have some example from the finite set. Okay, but of course it's going to be just like this in the finite, in the set operations, right? So we're doing union and intersection, but again this concept here of applying the basic step and doing the inductive step, it's just gonna be the same, right? So it won't be any different, but of course if there is an example coming ahead, we will have a look on that.
Okay, thanks.
Okay, any questions up till what we have covered so far?
No, it makes sense.
Okay, great. Then this is all I have for you guys for this tutorial. Since you guys haven't covered 5.2, I thought you guys have covered 5.2, but since you haven't covered 5.2, so this is going to be all it for 5.1. And I'll see you guys in the next tutorial.
Is it possible to just, I just want to see like, look, the next question.
The next question from 5.2. Yeah, so it's question number 1, 5, 9, 13,
No, I haven't done this.
25, 37. Okay, maybe I can write it in the chat. Where's the chat? Chat. So 1, 5, 9, 13, 9, 13, 25, 37. Okay. So this is for exercise 5.2. Okay, any questions, any feedback, anything that you would like to be included in the tutorial?
Is it possible to solve like some additional questions from the book?
Yeah, of course, but as I mentioned earlier, that you have to email me those questions at least like 2 days ahead of the tutorials, so I can just just keep that on top of my head.
Oh, okay.
Okay, if you guys don't have anything else, then that'll be it for the tutorial, and I'll see you guys in the next tutorial. Okay.
Okay, thank you.
Yep.
Okay, all right, bye guys.
Bye, man.
Goodbye.
All right.